Okay, let's try this again. Hi there, my name's John. Welcome to my live math stream. I did not advertise this one, so I don't know that too many people are going to be logged on, but if you are, that's great. I'm going to do some math here. Basically, the idea here is that I am going to run through this Barron's AP Statistics book. I hold a mathematics degree and with a emphasis in probability and statistics. So it shouldn't be too hard to do this, but I haven't been in a math class for over 7 years, so there's going to be some memorization things going on, etc. So what I'm going to do is I'm going to go ahead and take the diagnostic test. I'll talk a little bit about what I see going on as I go through it and why I might get the things wrong that I get wrong, right? And then what I will do is I'll go ahead and work through the rest of the book, and I will live stream the whole thing. My idea here, obviously, this is advertising for my in-person tutoring. I have a mobile whiteboard, and I've been vaccinated from day 2. So here we go. Okay, so for the next while, I'll go ahead and work from Barron's AP Statistics. I'm starting on part 1, the diagnostic test. This is where I get to see how much I forgot. I'll go ahead and read the questions and answer on the whiteboard when appropriate. This is a learning process for me. This is new. This is the first time I've ever done something like this. So here's where I'm taking my lumps. So please bear with me. Or don't and not learn math. All right, here we go. It is now 12:33 p.m. And sorry about that, I'm a little bit late. I meant to start at noon, but nobody knows that, so I shouldn't really apologize. Okay, here we go. Part 1, diagnostic test. Boy, that's not quite close enough, is it? I think I'm going to go with the single view camera here. That's a lot better, actually. Okay. There we go. I am starting right at 12:35. Starting time, 12:35. What's section 1, questions 1 through 40? Go ahead and answer these. Number 1. It is estimated that 56% of Americans have pets. However, favorite pet choice differs by geographic location. A random sample of pet owners is cross-classified by geographic location and pet of choice. The results are summarized in the following segmented bar chart. So we have the north and we have the south, cats, dogs, and other. And then obviously we have percentages for those. This is fairly standard. We have cats, dogs, and other. Obviously, other could be different in the north from the south, etc., etc. This is a fairly standard thing. The other category is sometimes problematic because, again, it could be, we could be comparing apples and oranges. We could be comparing ferrets to horses. But the big deal is that we are not talking about dogs. We're not talking about cats. We're talking about some other critter that we hold as pets. So here we go. Which of the following is an incorrect conclusion? Already starting with that negative. Okay. Which is incorrect? More pet owners in the South than the North answered other. Well, that looks true. That looks true. Twice as many pet owners in the North answered dogs than answered other. Okay. So that is basically asking, is this space right here double this space right here? And I'm not so sure about that. Maybe. It's hard to eyeball it. We need to see numbers. See, the number of pet owners in the South answered the same number of pet owners in the South answered cats as answered other. Again, it's kind of hard to see, but I would say that one's actually true. No. Hold on a sec. Okay, these do not look the same to me, but it's really hard to say. I'm leaning towards C. D, in both the North and South, the same proportion of pet owners answered dogs. That's definitely not true. Well, that's definitely not true. A greater proportion, E, is a greater proportion of pet owners in the North than in the South answered cats. Well, that's definitely true. Okay, so the same number of pet owners in the South answered cats as dogs. I don't see that as... We'll go with C. I don't like this question because it's really, this is not a comprehension question. This is how well can you look at a bar chart question. Let me see the numbers and I can tell you this for sure. But we'll say D is definitely incorrect. And this is fairly standard, to be completely honest, just in terms of the way it does become sometimes a bit of a judgment call. It's easy to know the correct answer when you know the numbers that went into the graph, right? Okay. Is there a linear relationship between calories and sodium content in beef hot dogs? A random sample of 20 beef hot dogs gives the following regression output. Okay, so we have a dependent variable is sodium. Predictor constant calories, okay, S R squared, adjusted R squared. I think this is Minitab, it doesn't particularly matter. Okay, which of the following gives a 99% confidence interval for the slope of the regression line? Okay, so this is one that we will need to go ahead and talk through. This is a good example of one of the memory games I mentioned before. So let's just talk a little bit about what we're talking about here. So what we're talking about here Okay, after reading this one for far too long and trying to decide whether or not I was going to talk about what we're talking about with the confidence interval of a regression line. I think I'm just going to go ahead and burn through the rest of these problems because daylight's burning. So these are the sorts of questions that will come across quite a bit. And it's really a matter of making sure all the numbers line up. Let me back up a little bit. Let me talk test strategies just a little bit here. Test strategies are survival. I'm going to go ahead and move to survival mode at this point because tests are about survival. It's about doing as well as you can on the test and taking that wherever it's going to take you. It's not necessarily about understanding. It doesn't necessarily matter if you cheat to get to the answer, as long as you're cheating in a way that demonstrates you actually understand what the hell's going on, right? Some would take issue with the idea that a test-taking strategy would be cheating. I'll let the philosophers figure that one out. But I am going to talk some test strategy survival stuff, right? So in this particular case, we can throw some things out right away. 2.861 versus 2.878. I don't see either of these numbers. Okay, so this would be the slope. This is going to be the 99% confidence interval. This is the 99% part. And we need to figure out, we would need to actually go to the, we would actually have to go to a chart to figure this out. I mean, nobody these days actually uses a chart to figure these things out. We actually just, I mean, you see how ugly this is? I could just plug it in my computer and survive, but I'm actually trying to get used through this stuff. So we're looking at a 99% confidence interval. That leaves 0.5% on either side. So we are sitting right about here. It's really hard to see in this particular graph, so I'm probably going to cut all this out. But this 0.995 is associated with 2.575 approximately. So 2.575 is entirely inconsistent with these numbers, 2.861, 2.878. Okay, I'm not quite sure what's going on with this one, so I'm going to be guessing a little bit here. We have the square root of 20. Those are going to be, we know it's going to be one of those. We have 2.61 versus 878. We have this 4592, which is SE conf, it's a coefficient of some sort. It's definitely not right. Yeah, it's definitely the average. I'm going to go with D, and I'm going to move on. I don't like that question. This is absolutely one of those memorization things. Again, what we're talking about with question number 2 here is the idea of the confidence interval of the regression line coefficient. Basically, this is one of the things that is constantly ignored once you get to the real world. Okay, moving on. In tossing a fair coin, which of the following sequences is more likely to appear? Okay, so in this particular question, basically what they're asking is if you're tossing a fair coin, what's the most likely of these outcomes? And so are you more likely to get 5 heads in a row, or are you more likely to get heads, tails, heads, tails, heads, tails in that order? And so the problem with that question is not heads versus tails. The question is how many trials you have. It's pretty clear that the most likely one is the one with the fewest number of possible outcomes. So we're going with A. There have been growing numbers of news stories about white Americans calling the police on people of color whose behavior is completely normal. A criminologist hypothesizes that the mean number of such incidences across the country is 2 per day. A sociologist believes the true mean is greater than 2 per day and plans a hypothesis test at a 5% significance level on a random sample of 50 days. For which of the following possible true values of mu will the power of the test be the greatest? Okay, I'm honestly not sure about this. We're getting into significance levels. We're getting into power. Again, this is one of those things that I worked in the real world for 7 years, and we never really talked about the power. That's a damn shame, to be completely honest. I'm not perfectly sure about this, but let's see if we can reason it through. Okay, so we're talking about a true value of mu. So what we're saying here is, what is the true level, the true number of calls per day? And if it's true that it's actually 2, yeah, I'm not sure. Okay, so the logic here is at 2, we go up and down 0.15. So for B, C, and D, we're all right around that 2 mark, which is where the first guy thinks it is, where the criminologist thinks it is. With E and A, we deviate more from 2. A deviates the most from true, so we're going to go with A. Keep in mind that these particular problems actually all have solutions worked out. So I'll be working out all of the solutions, and I'll correct everything that I messed up here or whatever. A simple random sample is defined by the method of selection, how representative the sample is of the population, whether or not a random number generator is used, the assignment of different numbers associated with outcomes of some chance situation, and an examination of the outcome. I'm not exactly sure what they're getting at on this one. I mean, a simple random sample, it's just any population that you have. You can take a simple sample of it And, you don't need to assign numbers. It can be binary. It can be yes and no, true or false, whatever. Yeah, I don't like this question one bit. A simple random sample is not defined by the method of selection, I don't think. Just definitionally, that doesn't make sense. How representative the sample is of the population is always a good question, but it doesn't define a random sample. The random number generator is just silly. The assignment of different numbers associated with the outcomes of some chance situation has to be the correct answer. And examination of outcomes is a big deal, okay? One of the things that you will learn the most in probability and probability theory is the idea that you have to let go of judging things by outcomes. If something has a 1 in 10 chance of working, and it works, that doesn't mean it was a good bet, because the other 9 times it will fail. So be careful of looking too hard at outcomes. Let's go with D. Can a shoe size be predicted from height? Yes. In a random sample of 50 teenagers, the standard deviation in heights was 8.7 centimeters, while the standard deviation in shoe size was 2.3. The least squares regression was predicted shoe size is negative 33.6 plus 0.25 times the height in centimeters. What was R, the correlation coefficient? And then it gives some numbers here. Again, this is one of those, you remember how to calculate a regression coefficient or you don't. I don't know how much I care. I'm going with the E. I'm not convinced of it, but this is one of those, boy oh boy, you have to have it memorized or you don't have it memorized. We could talk about what a correlation coefficient is. We know that height does not determine shoe size does not determine height. Age predicts both of them. Nutrition predicts both of them. So this is one of those somewhat silly, contrived examples. But I'm just going with E. Answers to 7 through 9 refer to the following situation. A researcher would like to know the oral diabetes medication she developed. I'm going to try that one more time. A researcher would like to show that the oral diabetes medication she developed helps control blood sugar better than an insulin injection. She plans to run a hypothesis test at a 5% significance level. 7. What would be a type 1 error? Again, I'm in survival mode here, but briefly, a type 1 error is seeing things that aren't there, and a type 2 error is not seeing things that are there. The type 2 error is more associated with the power of tests and stuff like that. That will all become clear later on. The type 1 error is sort of the easier one to see, and it's the one that most people control for, because seeing something that isn't there is generally a big deal than not seeing something that is there, okay? Okay, so here we go. What would be a type 1 error? Let's go true or false. The researcher concludes that she has sufficient evidence that her new medication helps more than the insulin injection, and that her medication really is better than the insulin injection. Well, that's fine. B. The researcher concludes that she has sufficient evidence that her new medication helps more than insulin, when in reality, her medication is not better. That's it. B. We'll read the rest. Always read the rest. Always finish them off. Even in a survival situation like this, just go ahead and finish them even when you're really sure of the answer, because as I said, seeing something that isn't there. And she said, It's there, but it's not there. So that has to be true. This has to be the problem. Okay, C. The researcher concludes that she does not have sufficient evidence, and her medication really is not. Oh, well, she's right. The researcher concludes that she does not have sufficient evidence that her new medication helps more than insulin injection, when in reality her medication is better than insulin injection. That is a type 2 error, and that's not the question here. The question is for a type 1 error. But this is it. I mean, this is the problem. It's sometimes we can't show a thing that's true. E. The researcher concludes that she has sufficient evidence that her new medication controls blood sugar level the same as insulin injection. In reality, there's a difference. Okay, so this is a nice little trick here. This is why I told you to go ahead and read through them all. This one made me think for a moment. The problem is we're not testing for equal, we're testing for better. This would be the same as the previous. This is still a type 2 error. What would be a type 2 error? Well, I think we're going to be able to find one of these relatively easily. A. The researcher concludes that she has sufficient evidence that the new medication helps more than insulin injection, and the new medication in reality, yeah, these are all exactly the same, so we'll just go right to it. We'll go to D. We'll go to D and not E for the reasons that I just mentioned. A, D. The researcher thinks that she can improve her chances by running 5 identical hypothesis tests, each using a different group of diabetic volunteers, hoping at least one of the tests will show her new oral diabetes medication can help control blood sugar level better than insulin injection. What is the probability of committing at least one type 1 error? I think that's a fantastic question. A, 0.5. Okay, this is a really good question. This is a good question. So if the chances of making one error is 0.5, that means the chance of not making an error is 0.95. To the fifth, 1 minus, we're going with C. And the reason for this is, we'll get into it later on. A financial analyst determines the yearly research. I'm going to try that again. A financial analyst determines the yearly research and development investments for 50 blue chip companies. She notes that the distribution is distinctly not bell-shaped. If the $50 amounts are converted to z-scores, what can be said about the standard deviation of the 50 z-scores? Okay, so a z-score, I'm trying to understand this question because a z-score is usually used to convert back and forth between normal probability distributions and the standard normal probability distribution. The standard normal probability distribution has a mean of 0, and a standard deviation of 1. People used to do this because it was very expensive computationally to do this kind of math. This is a dated question. We use z-scores for understanding, but not so much for day-to-day work. And what can be said about the standard deviation of the 50 z-scores? Okay, let's walk through these. I don't like this question. Wait, did I say I like it? It depends on the distribution of the raw scores. Well, yeah. It is less than the standard deviation of the raw scores. Probably because you converted, right? Converted everything to 1, so it's a smaller number. I don't get that. It is greater, same problem. It is equal, same problem. It equals 1. I don't think so. Going with A. A coin is, excuse me, a coin is weighted so that the probability of heads is 0.6. The coin is tossed 20 times and the number of heads is noted. The procedure is repeated a total of 200 times and the number of heads is recorded each time. What kind of distribution has been simulated? Okay. So these first 3 answers reference the sampling distribution, whereas the next 2 reference the binomial distribution. So I'm not quite sure about the usage of the sampling distribution on this one. Again, it's been quite a few years since I took a class. It's not a binomial with n equals 20 because that's each of the 200 different trials. I'm going with E on this one. Again, survival mode. I mean, it's definitely a binomial distribution because you have, heads or tails. And then you do that over and over again. If you do that once, it's a Bernoulli distribution. But once you start doing it over and over again, it's a binomial distribution. We will see how the answer shows up, but I think that's what it is. Okay. A 100-question multiple choice history exam is graded as number of correct minus 1/4. Let me read that again. A 100-question multiple choice history exam is graded as number correct minus 1/4 the number incorrect. So the scores can take values from -25 to +100. Suppose the standard deviation for one class's results is reported to be negative 3.14. What is the proper conclusion? A. More students receive negative scores than positive scores. Yeah. At least half the class received negative scores, not so sure. Some students must have received positive, some students must have received negative, or an error was made in calculating the standard deviation. Okay, I don't really understand this question all that well, so it's 100 questions. Let's take three scenarios. We get a 100 on it. We get a 80. And we really blow it and we get a 50. And so what's the calculation here? correct, the number correct minus 1/4 number incorrect. So 100 minus 0.25, 100, sorry, 0. Well, that's kind of rough. Okay, so let's go ahead and run this one more time. So we have more students receive negative scores than positive scores. And the question is, what does it take to get a negative score? So